All right, thanks everybody for joining. Welcome. We're doing a special session today on designing parts for strength. We'll be covering part orientation and fiber strategy. And look, this is the quick and dirty version, right? This is just a little kind of the bare minimum I thought would be needed to kind of start to understand these concepts. However, my colleague Dan Lawrence, who's on the meeting today, he conducts what's called our Jumpstart training. And if you're looking to invest in that, that's this, but on steroids. This is actually a very small snippet of the full day of training that comes with the Jumpstart. So if you are interested in that, contact Design Point and we'll be happy to help you out. So my name's Andrew Garchik. I'm an application engineer with Design Point for about 4 years, and I work in our additive lab. So I'll be conducting the session for you guys today. And the agenda, we're going to cover, again, part orientation, what I call sandwich theory. And then we're going to go into fiber strategy, how to route fiber, how to get the most bang for your buck. But some of the topics here is, what is the default fiber panel setting? How does bending theory play into this? How do you reinforce in the z-axis versus reinforcing in the XY plane? So we're going to go over all of that. And without further ado, I think we'll get started here and we'll jump in. So the first thing we're going to talk about is part orientation. So I've drawn these two diagrams here to help us out. This is looking at a part from the side. So you can tell from the layer lines here and the fact that the green bed is on the bottom. And you can see the Z plane is up and down, the XY or Z axis is up and down, the XY plane is left to right. And then the bottom view here, we're looking at it from the top. So you can see the bed is now surrounding the part on the bottom. We have the part in the middle, and this is looking at the XY plane. So when we talk about part orientation, it's really important, right? It could be the difference between your part being a success and a failure. It's super important in 3D printing, as 3D printing is very directional, right? So depending on how you place the part, it's really going to affect its performance. So to think about part orientation, I've developed something, and I probably stole it from somebody I got a long time ago, but I developed what I call sandwich theory, okay? And what sandwich theory is you think of the part like a sandwich, right? So let's say that this is a turkey sandwich. We've got the bread on top, the bread on the bottom, and then these layers in the middle could be your turkey, your cheese, your lettuce, whatever have you. We got like a nice looking sandwich there. So we're going to look at some different loading conditions and then how our sandwich is affected by those conditions. So first, let's start with looking at the part from the side here, and we'll look at a compressive load in the z-axis. Okay, so how does a sandwich do under a compressive load? Well, think about it. You put a sandwich on the table, you put your hand on it, you press down, and you let go. I mean, the sandwich is still there, right? It still exists. Maybe it's a little smushed, but it's still intact. So actually, in the z-axis, compression, a compressive force, or 3D printed part does pretty well in compression, right? Because it's like you're pushing everything together. But now let's look at that from the side. So now instead of having the force coming up and down, we'll come from the side. And now we have a compressive force from the side. So what happens to your sandwich, right? You got your sandwich, you go oop, from the sides, it buckles, right? Everything buckles and it all just pops out and it completely destroys your sandwich. So compression in the XY direction is actually not very good. And maybe we'll take a little side note here. Another thing to consider when you're talking about compressive loads, whether you're going in the Z direction or XY or whatnot, is infill. Because think about it, infill is open space. So if you're putting a compressive load on, you might actually cave in the infill. So if you're printing a part with a compressive load, it's important to know that infill is stronger from the top than it is from the sides. So if you have a compressive load like this coming from the side and you still have infill in your part, you may be setting yourself up for a disaster. And I've done it before, so I can tell you. However, if you fill in the infill and make this part solid, you're going to do better. And then really what I had said just before was if you really want to align your compressive forces along the z-axis. And then if you make it solid, that's really the best you're going to do. Make the part solid, no infill, align your compressive force in the Z, and that'll give you the best bang for your buck. All right, now let's look at the same thing from the top view, right? Or I guess that's actually going to be the same thing. Okay. So let's move on from there. So we did part orientation. We talked about sandwich theory. Oh, we didn't do tension, right? I'm sorry. So let's look at the opposite of that. I knew I was forgetting something. So now we're going to look at a tensile load. Okay, so now we've got a tensile load pulling the part apart from the top and the bottom. Well, what happens to your sandwich, right? If you grab the bread on the top of the bottom or whatnot, you pull it apart, it comes right apart, right? This is probably the worst case scenario you can have, between all these scenarios we're talking about. So the lesson here is tension is kind of it's the part is pretty weak in tension in the z-axis, right? But now let's look at that from the side. So now we're going to put a tensile force on, but coming from the side. Well, now what's happening to your sandwich, right? You take your sandwich and you try to pull it apart. It doesn't pull apart that easily, right? You got to break the bread, you got to break the turkey, you got to break the cheese. If you're going to split a sandwich with somebody, to actually take it and just rip it in half and make a perfect half, that's pretty difficult, right? So the lesson here is that 3D printed parts are really good in tension in the XY direction. As a matter of fact, that's your best possible scenario you can have. This is where you're going to get the most strength out of the part altogether. And then the second probably best is doing the same thing but a bending load. And it's very similar to what we just talked about. So probably a bending load is similar to just the way we're talking about tension there. Okay. So that is your sandwich theory. And the next thing we're going to move on to, told you it was the quick and dirty version, is fiber strategy. Okay. So how to lay your fiber in the part to get the most bang for your buck and why, right? Why is it stronger in certain directions than others? So we're going to move on to fiber strategy here. So the first thing I'd like to talk about is what the Markforged Eiger software does at a default, because it does something very interesting. When you flip on fiber and you don't change any of the settings and you just hit go and you go into your internal view to see what the fiber is doing, you'll notice that it creates these fiber panels on the top and the bottom of the part, right? And why? Why did it choose for my fiber to be there by default, right? It's kind of interesting. And to understand that better, you have to think back to engineering school and bending theory, okay? So again, we're talking about, we could use blue for this, some fiber going on the top of the part and the bottom of the part as a default. And what Markforged is assuming, and the reason why they're putting this as a default, is they're assuming that you might just have some sort of bending load coming from the top, right? Putting some force on the part. So they put these fiber panels in there to stiffen it, thinking everybody probably just wants a little bit of strength in that direction if they're adding fiber. But why, right? Why in the extremities? Well, bending theory, right? So if you think back to engineering school, you've got this bar and you have a force that acts on the bar. And what happens there is it puts the top in tension and the bottom into compression. Sorry, my mic has to reset every once in a while. So it puts the top of the part into tension and the bottom of the part into compression. And if you look at the forces on the part, you can see that there's the majority is on top in tension, and then as it passes through the bottom of the part, in the middle there's actually zero. There's zero force in the middle as it transitions from tension to compression, and then on the bottom you have also large compressive load. So by using these fiber panels on the top and the bottom, you're counteracting the part where the forces are the strongest that are acting against it. So that's the reasoning behind that. And what kind of fiber do you use, right? There's two types of fiber. You have what's called concentric fiber, right? Concentric fiber goes around the perimeter of a part, and it can actually encompass internal cavities as well. And then you have what's called isotropic fiber, which is that it's got the perimeter fiber, but then it fills in the middle. And then on every layer, it actually cross-hatches the fiber. So you get a pattern like that. Now that is ideal for what we call these fiber panels. This is ideal. There's 4 layers per panel as they change, and it takes 4 layers to go around the circle to get the full cross hatching. The way I think of this is like a trapeze artist, right? Well, let's back up for a second. There's 2 ways to possibly fill in a part, right? To get the maximum amount of fiber. You could do it isotropic, but you could also just keep filling in with perimeter layers. So what would be better for this type of reinforcement? And the answer is the first one. It's the panel that's got the cross hatching. And the way that I like to think about this is, think of yourself as a trapeze artist, right? And the fiber panels are your net. So do you want a net that actually lines up perfectly like that? Well, no, you might fall through the net, right? You want the net that's cross-hatched. So that's a good way to think of it. When the force is coming into Z, you probably want to think about using the more cross-hatched isotropic fiber panels. Now, let me draw that again. So now let's kind of look at the same thing, but we'll look at it with the isotropic fiber, right? And let's look at just one of the layers, right? So let's say the fiber is just going this way. So you could, oh, I'm sorry, I'm getting ahead of myself. So let's look at something else first. So what we looked at so far was a load in the Z direction, right? And that's what we want to use those fiber panels for, with the cross hatching. But now let's look at a load in the XY direction, right? Let's look at something else. So let's say first we have a compression load. Okay. And let's look at the 2 different types of fiber strategies we have, right? The isotropic versus the concentric. Well, if we look at that isotropic fiber and we look at one of the layers with the fiber going this way, is that going to be good in compression, that type of fiber strategy? Well, no, it's not going to be. And the reason why is what we already discussed. The fiber is not as good in compression as it is in tension. So when you put this force, a compressive force, you're putting each one of these bits of fiber into compression where it easily breaks. And a good way to think about this is actually just looking at a piece of spaghetti, right? So this represents a piece of your fiber. So if you put the fiber into compression, like this type of scenario, what happens? It breaks extremely easily. And that's what's going to happen to your fiber. But we can look at the opposite way, right? Now we take the piece of spaghetti and let's put it into tension. Well, if you don't bend it and you don't, it's pretty hard to break actually if you don't twist it or bend it in any way. So that's how the fiber is. The fiber is much, much better in tension than it is in compression. So when you are looking at a load like this, you really want to be stacking fiber, but you wouldn't want to use the this type of strategy. What you'd really want to do is fill in with more concentric rings to if you were trying to max out the fiber. Now here's another little sidebar. Think of it kind of like the bending theory again, right? Extremities. If this load is not compressive, but now it's a tensile load, using the concentric circles, that's going to align most of your fiber into tension, right? So this would be a good scenario. This is what you want. You want to use perimeter fiber for a tensile load, or for even if it was minus one of these, if it was just a bending load, that's what you want to do, right? Because think about it, if you use the isotropic fiber, when it goes, this way, that's really great, because you're putting the fiber into perfect tension. But we said each layer goes a different direction, right? So the other layers aren't going to be as good. So that's why it's better to just actually use a concentric load for that instead. So that's the gist of it, really. I think we covered the default fiber panels, did bending theory. We talked about Z reinforcements. What we didn't talk about
Compressive as
was putting fiber into compression. I forgot the other half again. Yeah. So that's tension. I mean, we did talk about it in one instance, but let's just talk about compression in general. Well, if we look at compressive load from the top, okay. Well, what's going to be a good strategy for this? Well, if we do the same type of panels we did before, it's not really going to work, right? Because it's simply going to push this panel down into the weaker plastic, and it's just going to fail by transferring the load to the weakest point. So the strategy you use for compression, when reinforcing for compression, is called stacked fiber, okay? So with stacked fiber, the trick is that you have to stack the layers all the way from the bottom all the way to the top. Or again, you're going to transfer the load to the weaker points. Now, this is an especially good strategy when reinforcing bolt holes. So this is very common. People always complain that when you tighten down sometimes they print parts, they give it to their machinist and they go to install the soft jaw on their CNC. They tighten down the bolt and they crush the part. So a lot of folks are looking for reinforced bolt holes for that reason. So if you think about it, if you had some sort of hole going through a part, the way you'd want to reinforce this, it would be with fiber rings around all the way from top to bottom. And now let's look at compression from the side. With the fiber we're talking now. Well, what happens there, right? It's the same story. You're putting your layers into compression, into buckling. So this isn't ideal, right? It's not ideal for a part without fiber. It's not ideal for a part with fiber. The fiber is susceptible to the same thing that the regular layers on, that they're just not good in compression in that direction, just like the spaghetti wasn't. So what do you do in this instance? Well, there's a couple things you can do. You can try to, nothing you could do with the fiber. I mean, it will have some strength in that direction, by the way. Like if you took a stack of spaghetti and you stacked it all together, I mean, you are going to get some force out of that, but not nearly what you would get in compression. So we covered compression on the top and the side. Now let's look at tension versus fiber. All right, well, tensile force from the side. This is, again, same thing as, it's very similar to what we were talking about before when it was without the fiber, but it's the same story. This is your absolute most ideal scenario. If you can align your tensile force in the XY and put down fiber, specifically perimeter fiber, to prevent it from pulling out, you're going to get very, very good strength off that part. But if you put the tension into Z, well, this isn't going to help you at all. There's nothing you can do fiber-wise with this. This is going to pull apart the fiber in between the layers, and the fiber connecting to the fiber below it, or the fiber connecting to the plastic below it, whatever happens to be below the layer, it's about just as strong as the plastic. So really, if your load is tensile and you can only put it into Z, don't even waste your time with the fiber. It's not going to do a thing for you. What you could do in this situation, some other strategies, not involving fiber, are if you're scared, well, I guess a shear would be more into the board, but if you're scared of some sort of shear failure coming in, you can print a hole and you could put a dowel pin through. Or in this exact scenario where you're really trying to reinforce for this tensile load, you could put some bolts and you put a hole through the part, you print the holes, and you put a couple bolts through. And that creates a clamping force, which is going to prevent your layers from delaminating, or at least make it much harder for your layers to delaminate. Okay, now I think I got it. We talked about the different loading conditions for fiber reinforcement. We talked about the different loading conditions without fiber, which you can see from everything. It's all very similar. And we talked about the different type of fibers for reinforcement, right? Perimeter fiber, more for an XY load, because in the XY, you want to align the most of your fiber and tension as possible. And we talked about for a Z force using, these fiber panels, on the extremities, and build from the extremities. If you need to add more strength, you could add multiple panels, but build from the extremities. And we also talked about compressive loads. We talked about stacking fiber, using bolts for reinforcement, and using dowels for shear force. So I think that's it for the session today. This probably isn't going to be the end all be all recording that I thought maybe we would get today. So I think we could open it up to questions right now. So if any of you guys have some questions, I know I was like a little all over the place with that, so I apologize. Again, don't quite have my rhythm down perfectly with this whole presentation yet. But let me open it up to the group. Do you guys have any questions on that stuff? Is anything really confusing? Did it make a lot of sense? What do you guys think?
Yeah, I mean, I think it made sense. One thing I was gonna ask was, I've
Sorry,
seen. Can you hear me?
can't hear you, Dan. I think I see you're talking.
Can you hear me now? Weird. Can
Huh.
I can hear
I
you.
can hear you, Dan, but
Yeah, I can't hear anybody.
I hear you.
Oh,
Yeah, we could hear you.
we'll wait. Can you hear us now?
Yep, we're back.
I was gonna ask is just as like a setup, is I've seen fiber striping before. When is that beneficial?
Yeah, I left fiber striping out of it. It just felt like it was like a little too much. But what that means, guys, I'll show you.
Just because if this isn't gonna be.
Well, we'll probably share this with Allied Maker, so it'll be
Mhm.
customer facing, but just not the end all be all one that I want to send to everybody. So what fiber striping means is instead of adding fiber to like every layer, you're going to add it to whatever layer, every third layer, every fifth layer, every second layer. So the fiber would be kind of more spread out. And you can do the striping with concentric fiber, or you can do it with isotropic fiber. So I think it just depends what you're trying to accomplish. You have to look at the loading condition. Are you trying to be stronger in Z? Or are you trying to be stronger potentially in X, Y? And then you would decide the actual characteristics of each one of these layers. But it's a real fast way. You basically just put it in and it goes boop, 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 puts fiber on about every other layer. And certainly, it's going to give you reinforcement in the Z. It's going to give you reinforcement in the XY because it's a combination of, perimeter fiber and potentially isotropic fiber if you fill it in with that instead. But I think it's also useful for torsional loads. So I think if you had something that was torsional and it was kind of along the full part, then that would be something to consider. Another thing is cost. Sometimes you just fill a part with fiber and you go, whoa, $100 for that? Like, okay, let's just cut that in half. So you might just use fiber striping just as more of like an economic tool to just say, all right, let's just cut the fiber in half and still spread it out homogeneously throughout the part and see what that metric looks like.
Mhm.
Even another use would be if you had a part that was like uneven.
Yeah, this is a really good one.
Yeah, I'm glad you brought this. This is actually good. So the way that I would look at a part like this is I would look at this as two different parts. And let's just say for what we're really looking at here is this is really, let's say there's like a bending force. So we're looking at Z reinforcement, right? Like we were talking about at first. So the first thing I do, and mentally, I break this up into two parts. Okay. So there's a bottom of the part, and then there's a top of the part. So on the bottom of the part, what you would do is those fiber panels, like I was talking about, that have the cross hatching in them. So put one on the bottom here and one on the top of this other area. One important thing with these panels is that they're even, right? You don't want imbalance because if you have different size panels or different strategy, different fiber routed, you could create some sort of imbalance in the part where it's not going to function that well. So the bottom here you can see is very well balanced, right? I'm putting two panels that are of equal size and shape, and the part is, the geometry here supports that. But then when I come up into this top part, I can't do that anymore, right? Because if I do a panel down here and I do a panel up here, now I have an imbalance. So one thing you might do in this situation is the fiber striping, and then you kind of just, you kind of keep adding them as you go. So it doesn't have such a big imbalance, kind of builds that way. So that's how I would use fiber striping. Dan, any thoughts on that?
No, I like that. Another question you might have gotten is when talking about sandwich panels, is there a recommended amount of layers to add of the
Sure.
panels?
So the sandwich panels are the fiber panels. That's
Hmm.
what I've been talking
Sorry,
about. I've been
I used the wrong
specific.
term.
No, it's cool. No, because they're called sandwich panels, but for the purpose of this discussion, because I had sandwich theory in the beginning, I didn't want too much sandwich, so I just called them fiber panels.
Maybe
But
change sandwich theory to hoagie theory.
hoagie theory. There you go. Hoagie theory. Perfect. Right. I didn't want too much sandwich. So I'm sorry, Dan. What was your question again? No, I lost it.
Is there a recommended
Oh,
what
uh,
is like how many layers of the panels do you add for the isotropic layers? Is it do you have like a recommended? Is it too much, too little?
sure. So when you're looking, remember, so this fiber panel or sandwich panel, as we call it, it's made of 4 layers, right? And each one, like I mentioned, not sure how far you guys can see on this board. I can just erase this now. So on the first one, the fiber goes, straight up and down. The second one, it's angled. The third one goes straight across, and then the fourth one, it goes the other way. So when you combine 4 of them in total, that's the full 360. That's the full cross hatching. And then once it goes to the fifth one, it would start repeating the same thing. So in an instance like this part here, when I say I'm going to put a panel on the bottom and a panel on the top, what I'm talking about is 4 layers that are cross hatched that combine to form that panel. So panel equals 4 layers. Now, if this load was larger and they said, this is a fairly big load, bending load here, I might double my sandwich panels and then add a second one. But what I'm saying is when I'm adding a second one, I'm adding a second set of 4, right? You want to go 4, 4, 4 because you want it to have all the layers of the cross hatching. Now, that being said, if you had 6, would it be the end of the world? Not really, but that's just how you kind of want to think of it in sets of 4.
Mm. Can you change the angle?
Yeah, this angle, this is the default. It's set to kind of go 1, 2, 3, 4 around, but you can change that angle to anything that you want. So, for example, maybe you've got part that looks, I don't know, something weird, something that's got different directions of some kind. Okay, so like how you like that part. So what you could do now is you could pick and choose those angles of your panels. So you could have maybe on, every other layer it switches, right? So, I mean, you got your perimeter fiber, which is definitely going to go around first. But then you could choose, whatever angle this is. You could have some coming this way. And of course, it couldn't be on every layer, but you could have one layer where it supports kind of this section, one layer where you got fiber going that way, and different layers you can actually be sending your fiber off in different directions. It would have to be on separate layers though, but you can align the isotropic fiber fill in any direction that you want.
Mm, cool. Anybody else have questions?
If there's no questions, what do you guys think of just definitely I got like mixed up in my head a couple times and I had to kind of go back a little bit. Did it flow well enough to make sense or did it get a little confusing?
It flowed well enough for me. That's
The guy's
Yeah.
right, but you can already teach
Yeah.
it.
I felt like it was good. Like you said, it was the quick and dirty version of it. So obviously, like you're not going to go into super detail. So for that, I think it was good. I mean, I got a lot out of it.
Okay. Thanks, Carly. What about you, Breland, Travis? Were you guys following? Was there some points where you're just like, oh man, he's jumping around too much. This doesn't make sense anymore? You guys are both muted.
Sorry. Yeah, I'm muted. I was gonna say, no, I think it was pretty straightforward. I think it made sense to me. It's
Okay.
definitely, definitely pretty straightforward. So, I mean, it was just a little part where you just got tripped up, but other than that, everything was fine. I think it was completely understandable.
Thank you. Yeah, I think it would benefit me to go back and like really think through the order of things. It's definitely a couple things were like out of order and it could have just flowed. I kind of got it all in, but it was a little sporadic. It wasn't like all in perfect order.
As a recommendation, if you want to step to your left a sec, so you can look at your list. Oh yeah. So we could do what you could do is for section 1, you could do part orientation, sandwich theory, but then have like another subsection so you don't forget, where it's like here's compression and the X, Y, and the Z, and here's tension in the X, Y, and the Z. And then do the same thing for fiber strategy, where like you write it down. Maybe you're not showing them the agenda, but like you write it down so you don't forget it, so you don't skip over to the next letter before doing that section of tension or compression. That might be
Yeah,
helpful.
definitely. Yeah, I think I just need a better agenda for myself. Like there was one point I was actually going to pull out this piece of paper and I was going to show you like a layer, like tension. Very hard to break it. Actually, my arm's injured, so I physically literally can't break this piece of paper. And then compression, right? So I was going to use this for the top part, and then I was going to use the spaghetti for the second part, and I totally forgot. So I definitely need to be writing stuff down and, in detail, like you said. But
I think it's still very good, like as far as content wise. It was
Okay.
understandable.
Okay, so we should send this to Mac.
If you'd like to.
Hi, Mac. All right, we're sending it.
Yeah. I mean, I think now that you've kind of caught yourself on that step where you just had a hiccup and got more clarity, that's something that's going to stick with you. So, yeah, it's like kind of a reminder, like Dan was saying.
Yeah, just need some better agenda, like more detailed, like a very, very detailed agenda. So I could just go step by
Sure.
step by step.
Sure.
Yeah, just got to figure out the order. Yeah.
Yeah.
Okay. Well, thanks, guys. I hope you got some good value out of today. And if you run into something and it's a little like unclear, you're like, well, Andrew said this, but this doesn't make sense. Give me a call anytime. We can always look at a part, go over anything together.
Cool. Thanks, Andrew.
Great. Thank you.
You're welcome, guys.
Yes. Thank you.
All right. Have a good afternoon.
You too.
Too.
Yeah.
Yeah.
Bye.